Okay, we've actually worked with transformations before, just haven't called them transformations. We're talking about that and combining variables. So here we're just given a data set, 1, 2, 3, 4, 5 shown here. And if we were to add, let's just say 15 to every point in this data set, we would have 16, 17, 18, 19, and 20. If we add 15 to every data point. So what that would give you is something in this region. You'd have one there, one here. Okay, so the mean of this distribution would be 3, because the mean of 2 and 4 is 3, the mean of 1 and 5 is 3, and the mean of 3 is 3. By the same principle, the mean of this distribution is 18. So if we added 15 to every data point in this distribution, the mean goes up by 15. Okay. Now, if we added 15 to every point in this distribution, the spread of this distribution doesn't change. In other words, how much these data points are spread apart is not changed. It looks the same as this. Okay. So the standard deviation would stay the same along with the other measures of spread. Okay. So now let's say, what if we multiplied everything by 5? This would be 5. This would be 10, 15, 20, and 25. So I have one here at 5, which you can't see. I have one here at 10, 15, 20, and 25. Now the mean of that distribution is going to be 15. Kind of by the same reason. The mean of 10 and 20 is 15. The mean of 5 and 25 is 15. So the mean of this was 3. The mean of this distribution is 15. So it has been multiplied by 5. We multiplied every term by 5. And the mean changes by a factor of 5. Now, if you look at the spread of this, doesn't have the same shape as this. It's now more spread out. And where a typical difference from the mean was about 1 here, the typical difference from the mean here looks to be about 5. Okay, so the standard deviation has also been multiplied by a factor of 5. Okay, so adding a value to a distribution affects the center but not the spread. Multiplying a distribution by a value affects both the center and the spread. So we'll give those some names in a minute, but that's called transformations on a variable. Now we're going to talk about combining two variables. In other words, let's just say this is distribution x, and this is distribution y. Now if we're interested in adding values of x to y, and what we would get, we'd get something kind of out here. Well, let's just see what we get for this distribution. The smallest value would be 0. The smallest value of y would be 15. So when we add those, we would get 15. The largest value of our distribution x plus y, I'm working with x plus y here, would be 12 plus 20, which would be 32. Okay. Now, notice that I'll just work with range here, which is range is a measure of spread. But we can kind of tell that the spread's getting larger here. The range is 12. Here the range is 5. Here the range is 17. Okay, so it's gotten bigger. One thing that we'll actually learn is that if you add a normal distribution to another normal distribution, you're going to get a normal distribution, even though doesn't look like it there. Okay, x plus y is going to be normally distributed. So spread gets larger. The center, as you would probably guess, is just, we can add the mean of that plus the mean of that, that gives us the mean of this. Okay? Now, if we're going to subtract these values, I'm just going to do the bigger set minus the smaller set. So the smallest value that we can get when we subtract something from this set would be 3. The difference between 15 and 12. Now the largest difference that I could get would be 20 minus 0, which would be 20. And I'm trying to put these on the same spot. 3 is about here, 20 is about here. So also the difference of two normal distributions is normal. Yeah, it's supposed to end about right here. But what do you notice about the spread of this? The spread is also bigger. Even though we're taking the difference between two distributions, the spread is getting larger. So now we're going to look at some formulas. Hopefully that kind of give you an idea of where these formulas are coming from. First thing we're going to work with is our distribution x plus a. Now what x is our distribution, and a means I'm adding a constant to every term in that distribution. This is the first example we looked at. So we know that the mean of x plus a, if I add a to every term in the distribution, I get the mean of x plus a. Just like the first example, when we had 1, 2, 3, 4, and 5, and we added 15, that was the same. Added 15. A is 15. We added 15 to every data point. Then the mean of that was 3, which was the mean of the first distribution, plus 15, which was 18. Okay. Now, the standard deviation of x plus a. Remember that the standard, if we added a term to the distribution, it did not change the spread of that distribution. So that's just equal to the standard deviation of x. A does not affect the standard deviation of x if you're adding it. Okay, now we'll look at b times x, or x times b, which means we're multiplying every term by b. So the mean of b times x, we can just multiply b times the mean of x. Okay. So going back to our example, when we multiply everything by 5, our original mean was 3, and our new mean became 15. And also the standard deviation of bx is also b times the standard deviation of x. The spread also was changed because the how much those values were spread out also increased by that factor. Okay. One thing to mention here is if you're ever working with the variance of bx, because you're working with squared units, is b squared times the variance of x. Okay, but that makes sense to go from that. If you were going to square this value, you would square b and square that, which would give you that. And we know that the standard deviation squared is the variance. So now what we're going to work on is x plus y and x minus y. That means if you're adding values from x to the distribution of y. Now, neither one of these are constant. These are both variables. They're separate distributions. That's what we just looked at. So the mean of x plus y is the mean of x plus the mean of y. And that's what we showed earlier, is you can just add the centers of those distributions. that's where the center of the sum of those are going to be. And that's one that we usually don't mess up. That makes pretty much sense to us. So the standard deviation of x plus y. Now you might think that you could just add the standard deviation of x plus the standard deviation of y and you could be done. Well, we can't really exactly do that. We have to work with variances here. So we can add variances though. So what the variance of x plus y is the variance of x plus the variance of y. And if we wanted to know the standard deviation of x plus y, then we could take the square root of both of these, and I'll actually do that. The variance of x plus y is the square root of the variance of x plus the variance of y. Now, we need to be careful here. We can only take the standard deviation of, combine these two standard deviations the way we did if x and y are independent variables. In other words, a value of x does not depend on the value of y. Okay, so if you're working with SAT math scores and SAT verbal scores, you really shouldn't be able to combine them like this, and sometimes you may see a problem like that, but they need to be independent. Those two really aren't independent. So if they're not, you have to use another formula, which is not in the AP Stats curriculum. So you should always use this formula, but you should always make sure that they state that it's independent. Otherwise, say something about that. Now, the last thing we're going to do is x minus y. So the mean of x minus y, just like you would think, is the mean of x minus the mean of y. And lastly, the last thing we'll do here, the standard deviation of x minus y. Again, we can't work with standard deviations. We need to work with variances first. And remember, when we were subtracting those distributions, the spread still got larger. So we're not going to subtract these variances. We're still going to add them. Just going to look the same, exactly the same as this. So the variance of x plus the variance of y. And again, if you want the standard deviation, take the square root of both sides, and you get that. Okay, so those are all of our, I guess you can call them formulas. They should make some intuitive sense, but that's all of our transformations and combining variables. I'll show one example here. Let x be a normal distribution. I'll just do the mean is 100. No, let me do 100,000 observations of this random normal distribution. The mean is 100 and the standard deviation is 10. Observations of y, which is, it says standard deviation is 50, or the mean is 50, standard deviation is 5. So before we run this, we can kind of understand. I'm going to do the difference first. Well, I'll just do the difference and that'll be it. The mean of, I'll call z, x minus y, which means we're just taking all of the values of x and subtracting all the values of y. The mean should be about 50. 100 minus 50. And the standard deviation we would get from taking the variance of these, which would be 125. We don't subtract them, we add them, which would be square root of that, which would be 125. Or add those together to get 125. And then the standard deviation of x minus y should be about the square root of 125, which would be a little over 11. So let's let z equal x minus y. I'll do a histogram of z so we can see it. And then just let me state the mean of z and the standard deviation of z. Let's see what we get. We said the mean was going to be 50. Notice that it was 100,000 observations each. We get a mean very close to 50. These are just random, 100,000 random observations. We added them together. And again, the standard deviation is slightly over 11, which is what we said. And this is what it looks like. Centered around 50, standard deviation slightly over 11. So realize that the last time I've already mentioned it, but if you have two normal distributions and you subtract them, then that distribution is also normal. You get a good idea looking at this histogram here.